My name is Sofie, and I am a big data architect at Verint. And today, I will present you in this talk our very innovative big data analytics platform. And the platform is actually not just a theoretical use case. It's a real platform that is already in production, and I'm proud, really, to stand here and tell you about. So I will start with a few words about Verint. And I think this sentence is probably describe what we do at Verint in the most precise way. Take a minute to read it. In other words, we are building, implementing systems that help organizations to prevent, to detect, and to investigate crime, terror, cyber threats. And actually, our big data platform is one of those tools. So, what does it do, our big data platform? The story. We are all interacting with each other, leaving our digital footprints all over the cyberspace, generating terabits of data out of many applications, many network events. So the question is how we pinpoint the bad guys out of those billions of entities that we see in our network. And one probably asks why we are different from other platforms, why our challenge is more unique than others that likewise collect masses of data, analyzes, and searches for anomalies. Well, we think we are different because everything is fluid in our system. It's fluid because we are collecting entities from many different domains and types, whether it's IP address or server or domain name or email address or even a website. And because the inventory of characteristics of each entity also changes from time to time, what perhaps seems irrelevant now, one of the characteristics may become very important later on. And the behavior that we are trying to detect, it's also very fluid, and it differs from one domain to another. Investigating drug dealers is not like investigating cyber threats, and investigating cyber threats is not like drilling into the website and investigating web crimes. So the behavior are also dynamic, not only in the sense of different domains, but also because the behavior is changing from time to time, and we also need to adjust our algorithms from time to time. And another thing to note is that the behavior itself, the patterns that we are looking for, are not so obvious. So how we can define a crime pattern? What is crime pattern? What is terror pattern? It's not so obvious to define and to characterize. Also, the data sources are very diverse, and they're changing dynamically from one site to another, from one deployment to another deployment, from one domain, one customer to another. And the algorithms we use are also very different, as already mentioned. So are the end users. The end users coming from different domains, coming with different skills, and most important thing that our systems are mostly deployed on customer premise systems, which makes it which we have to make them very scalable, very secure, and we usually saying goodbye to our system just before they ship to our customers with the almost no access to the systems, with no debugging option, no monitoring options. So this fluidity is really what makes us different and what makes the intelligent system different from other systems. And the main thing that we want our use case be generic. We want to build one system that answering all domains. So what we are doing, basically, we are investigating those entities, those network entities, and we're trying to detect out of those billions entities the one that is unique, the one that have suspicious behavior. So, how do we do this? It sounds very simple and basic, but we actually understand that the pattern of doing this is very common to all our use cases, to all domains. So it's actually very generic formula. We need first to learn and model every entity in the system. Then we need to find the common background among all those entities. And then we can subtract the background from each and every entity and reveal the unique attributes of the entities. So, how we did this? From concept to technology. These are only concepts, and I'm going to dive into each and every of the concept, but just to give a wide picture. So we have stream and batch in our system. We are combining stream processing and actually investing many efforts to process the data in stream, to shape it, and to prepare it for further batch analytics. We have multi-stage processing, and actually multi-stage processing is the key concept of our system, is the basics that we understand and what makes this system very generic and usable in many other cases. So multi-stage processing is when you have a very complex algorithm that cannot be, or it's not feasible to calculate as one monolithic block. Then we have to split this monolithic block to many simple blocks, allowing each block to scale out, and each block in this calculation is simple enough to calculate and is feasible. So actually, this is the highlight of the platform, breaking one monolithic calculation to many small calculations. And another thing, if you have one algorithm, it actually produces one output. But when you break down this algorithm to many small algorithms and small blocks, then you can output different insights comparing to one insight that you have in a monolithic algorithm. You have now many other outputs that are interesting as by themselves. So, another concept is also very interesting, and it's multi-dimensional time window. We are processing our simple blocks in different time resolutions. So we can aggregate data in hourly basis and in weekly basis and monthly basis. It's not only that this approach allows us to divide the monolithic block to many simple blocks, it also allows us to reveal insights that perhaps we couldn't reveal them before when we had only one introspection of one time frame. And I can give you an interesting example. If you know all what is SIM card, yes? So swapping SIM cards into your phone mobile is actually something many of us did. But if swapping SIM cards becomes something that is pattern that repeats itself from time to time, from week to week, from month to month, then it might be interesting. Then it might refer to someone that uses the SIM swapping for his illicit activity. So if we're looking into daily routine of a person and see that the person swaps his SIM card into his phone, then okay, perhaps he gone to vacation and used another SIM card, the local SIM card. But if we are tracking this behavior in repetitive method, then it's very interesting. So, this is the last concept, but also very interesting. The diversity of data sources and entity types and many blocks and many insights that I described you before actually poses a very interesting dilemma to our presentation layer. How we should present all those insights with different schemas and different data formats coming from different data sources? Well, this I also will describe later. So, we are starting with stream and batch. The in-stream processing is actually our front shield. We are observing massive amounts of data arriving from Kafka topics, but we need first to extract interesting parameters, interesting attributes. We need to shape the data, format the data from receiving from different data sources. And then we are already performing an initial processing. We are doing aggregation for short time windowing and creating an early insights. So, this diagram actually looks like the diagram we already seen before, several slides. Same pattern, we're trying to reveal unique attributes out of billions of entities using many simple blocks. So this diagram is more technical, and we can see all the building blocks. So the upper row of this diagram demonstrates how we extracting insights from individual entities. So, and doing this is also simple because single entity, we can partition the data by entity ID, just like any other partitions. So doing it for every individual entity is pretty simple when the task of processing divided to many small blocks. The low level of flow is actually crowd profiling, how to compute a common background of all the entities that we are see in our network. And the right part of the diagram is actually subtracting the background, the common background from every individual. So you can probably understand from the diagram that when you moving to the right side of the diagram, you can see that the data is decreasing, and it's decreasing seriously. We have significantly less data from stream to daily to weekly aggregations. When we have less data, it means that we can apply more complex algorithms. So less data, more complex algorithms scalable, and feasible. The low part of the diagram is also pretty simple, because calculating a common background is not necessary that you need all the data set. You can just sample and calculate the background from percentage of the data. Again, calculating the data on small parts, also feasible, scalable, and can be partitioned. And you also can see that each block has its own input and has its own output, has its own data scheme that it consumes. It does not depend on the general data schemes, what makes the management of a schema more easy. And actually, if we wish to add another block, the new block will not have to be aware of all other data formats and data that is coming from other blocks. So this slide is actually now explains what concepts made it possible to build this processing. So we already saw that we have simple building blocks, we have flexible schema, and we have chain processing and dependency management. The blocks were chained together using our predefined model of execution graph, and chained together with a dependency manager. This is just to illustrate that simple block diagram became a more complex and more fancy diagram with many other simple building blocks. Okay, multi-dimensional time windowing. Reveal insights in interesting routines that were not obvious if calculated only in one-time dimensions. I already described you the SIM algorithm, but we are doing time windowing not only to reveal interesting insights, but we also use this scheme to manage our processing time windowing, our algorithms, because there are some algorithms that can run in high resolution in aggregations of weeks and months, and when they do run in those resolutions, we can keep the data of weeks and months and retain it practically forever. But algorithms that run for a short period of times, for days or hours, they have more precise data and they can apply more precise algorithms, but this data is apparently less important and we are purging this data more frequently. Okay, so exploration and visualization challenges. From one side, we have a very flexible schema. We have many insights that we want to visualize. We have many domains that we want to use for our systems. We have many different end users with different skills. Some of them are investigator, and some of them have more knowledge in network and in traffic analysis. And we want to build one generic layer for all domains that's capable to deal with flexible schemas in interfaces. So to take all the data and to index it in one database, and no matter what the database is not practical, is not feasible from one side. But from other side, we want to allow our end user to make an interactive queries to get the results immediately. So without the capability to index all the data and being aware of the other distributed query engines like Spark SQL and Hive and Presto, and being aware of their limitation in terms of execution times. They're not so interactive as we hope they be. So we had to think of another approach, and we built a two-phase query engine that actually, in its first phase, scans the data using the regular partitioning scheme, for example, partitioning by day, partitioning by entity, and those outputs of basic scan are indexed in intermediate database, Elastic, and then when the data is indexed in Elastic Engine, it's now free for use to our end users and available to different types of queries, different type of search criteria and parameters. So this diagram actually illustrates all the technologies, all the open sources we are using. We have Kafka as our main message bus with Avro and the schema registry management. We're processing the data in stream and in batch with Spark. We have persistency, where the database of our insights is HDFS, storing the data in Parquet formats. And we are querying the data using, again, Spark SQL and Elasticsearch, as I've described in the previous slide. The multi-stage processing and chaining are managed using Airbnb, Airflow, open source by Airbnb. So we are really using the leading edge technologies, the open sources, but we are also invested a great deal of code and efforts to bind all those technologies together and make our platform to be one holistic and generic platform for all different domains and expertise. Thank you. This is my slide. You are welcome to contact me.